Hello, I am Alexandros-Apostolos Boulogeorgos from University of Piraeus, and I'm going to present you our work on Pathloss modeling of a reconfigurable intelligent surface-assisted terahertz wireless system. The agenda of today's presentation consists of 4 parts. In the first one, I will give an introduction emphasizing the background technologies, motivation, contribution. Then the system model with its assumption will be presented, followed by the Pathloss model and our results and conclusion. In the first part, introduction. The main question is, why do we need terahertz wireless communications? So let us look in beyond 5G applications, such as in-body sensing, augmented and virtual reality, 3D printing, and robotics. What are they require? They require compactness, high data rate, reliability, and low latency. However, if we look at the spectrum right now, the 4G spectrum from 3 kHz to 6 GHz, we will see a number of applications there that create a spectrum scarcity problem. To deal with this problem, 5G opened the door to the spectrum from 6 GHz to 100 GHz and move some boundary-hungry application to these frequencies. However, is it enough? In order to achieve their communications, we have a contiguous bandwidth of 7 GHz. We need to implement a complex transmission schemes and massive MIME. But are 7 GHz enough? According to Cisco, they will be not. Till 2030, the telecommunication traffic is expected to increase for about more than 10 times or about 100 times. So what we were expecting to do in 6G, we're expecting to open the door to the terahertz frequency band, where you can find 20 gigahertz of continuous bandwidth, and you can use low complexity transmissions to send your messages to support those applications. Now, this band, the main characteristic of this band that we need to think about is the high pathloss, as you can see in the left figure. In order to deal with high pathloss, we use high directional antennas. However, due to the high penetration loss, this band suffers from blockage. To avoid blockage, we use a new technology that we refer to as reconfigurable intelligent surfaces. Reconfigurable intelligent surfaces are surfaces that consist of a number of passing elements controlled by diodes or nano-network control agents that are coordinated by microcontrollers. And they are capable of manipulating the incident electromagnetic wave in order to absorb, steer, focus, split, reflect, or polarize it. The main idea here is to use RIS to avoid blockage. In more detail, if you have a blocker that is between the access point and the receiver, you can redirect the transmission through an RIS and let the receiver, the end user equipment, to have a reliable communication. But in order to achieve this, we need to build our toolbox. In other words, we first needed to create an end-to-end Pathloss formula. Motivated by this, in this work, we present a system model for resource-sensitive terahertz wireless communications, and we employ electromagnetic theory to derive a general expression for the end-to-end Pathloss. Building upon this formula, we determine the phase shift that each RIS element should impose in order to steer the beam radiating from the RIS toward a desired direction. And we present a type Pathloss approximation that enables the performance analysis of our RIS-assisted terahertz wireless systems. Our work is expected to contribute both to channel and RIS modeling to help in creating a strong theoretical framework for performance analysis and become the pillar of creating an optimization framework. Concerning the system model that we used, we assume a simple system model where an access point wanted to communicate with a user equipment through an RIS that consists of m times n element that horizontally, so they are separated with a distance dx, while vertically dy. We took into account the antenna gain of the transmitter, the particularities of the terahertz channel, namely spreading loss, molecular absorption loss, and the high directionality. The RIS units, radiation patterns, and the reflection coefficients, the distance between the access point, the RIS, and the RIS and user equipment, as well as the RIS stimuli and the receiver's antenna gain. We assumed that the system is operating in the far field and that there is no coupling between the RIS units. Based on the aforementioned system model, we derived a Pathloss expression that you can see here, and it's analyzed in the paper. I don't want to lose any time on this. And we find some simple expression that show what should be the phase shift of each reconfigurable intelligent surface unit cell in the incident electromagnetic wave. Our results. In the first figure, you can see the Pathloss as a function of the temperature and relative humidity for an RIS that consists of M equals N units equal 100, operates in 380 gigahertz. The distance between the access point and RIS is 1 meter, while the distance between the RIS and the user equipment is 10 meters. You can see here for a fixed temperature, as the relative humidity increases, the Pathloss also increases. Moreover, for a fixed relative humidity, as the temperature increases, the Pathloss also increases. In the figure in the middle, you can see the Pathloss as a function of the temperature and frequency. You can see here that for a specific frequency, as the temperature increases, the Pathloss also increases. However, it's a slight increase in comparison with the increase that we have for a fixed temperature as the frequency increases. Moreover, you can see that there exist two frequency bands around 380 and 450, where the Pathloss is maximized. This is happening because around these bands, the molecular absorption is maximized. The same result is given in the last figure, where we can see the pathos as a factor for the frequency for different sizes of RIS. What we can see here is that as the RIS size increases, the pathloss decreases. This happens because as the RIS size increases, its gain also increases. Thank you very much.